Let's review solubility equilibria in Ksp. With solubility equilibria, we deal with the fact that insoluble salts are actually a tiny bit soluble. The solubility product, Ksp, is the equilibrium constant between the undissolved solute and the not many ions. For example, on the left we have the insoluble salt in solid form, in this case nickel 3 hydroxide. And then on the right side we have the dissolved, that is aqueous, ions in the ratio of 1 nickel 3 ion for every 3 hydroxide ions. And we write the equilibrium constant expression as what's shown here at the bottom. Notice that the insoluble salt, which is a solid, does not appear because we don't write solids in equilibrium constant expressions. So let's try this problem. Copper 2 azide has a Ksp of 6.3 times 10 to the negative 10th. Find the solubility of copper 2 azide in water in grams per liter. I'm not exactly sure how to start here, so let's write the formula for copper 2 azide. When it dissolves, which of course not much of it will because this is an insoluble salt, but the bit that does, we will have the ions formed in the ratio of 1 copper 2 ion for every 2 azide ions. The Ksp value is given, so we know that we can write that equal to the concentration of the copper 2 ion times the concentration of the azide ion squared. Okay, so far so good. In plain old copper 2 azide in water, we can see from the equation at the top that there will be twice as high of a concentration of azide as copper 2 ion. So I've written that here on the right side of the screen. The concentration of the azide ion will be whatever the copper 2 ion's concentration is, doubled. Okay, so this is key. Here's what we're going to do. We're going to let X equal the concentration of the copper 2 ion. Here's what's going to happen. We bring the Ksp down. If the copper 2 concentration is equal to X, I'll bring that down as X, and then let's look at the expression on the right side of the screen here. If the copper 2 ion concentration is equal to X, then the azide concentration is equal to 2X. And then I bring the squared down as well, which means this simplifies to 4x cubed. X times the quantity 2x squared is equal to 4x cubed. We can solve that for x. And what is x? Well, you can see in the upper right portion of the screen we've said, oh, well, x is the concentration of copper 2 ion. It's also equal to the concentration of the copper 2 azide that has dissolved. If you look at this equation that we wrote first, right up here at the top, if we know this value is 5.4 times 10 to the negative 4th, then because this coefficient is 1 and the coefficient on the left is 1, then isn't it true that this concentration of stuff that has dissolved is also 5.4 times 10 to the negative 4th? That is, in one sense, the answer, except it's very clearly stated in the problem that we don't want moles per liter, we want grams per liter. And that's child's play to convert to grams per liter. We simply find the molar mass of copper 2 azide and we calculate grams per liter. Let's try another one. Let's find the solubility of zinc hydroxide, and there's its Ksp, in a solution buffered at a pH of 11.43. Firstly, zinc hydroxide is an insoluble, and when we say that it's insoluble, we mean that it's just a little tiny bit soluble. Let's write the dissociation equation for the bit of zinc hydroxide that does dissolve. And it's of course going to look like that. We're going to get the ratio 1 zinc ion for every 2 hydroxide ions. There's the Ksp value. We can fill out the equilibrium constant expression by writing concentration of zinc ion and then the concentration of hydroxide ion raised to the second power. Now it turns out that this problem is actually easier than the one before it. And that's because if the pH is buffered at 11.43, that means it's constant. And if the pH is constant, then the hydroxide ion concentration is also constant, which means we can calculate the hydroxide ion concentration. I've skipped a few steps here, but I'm trying to show you that we've got here, this is 10 to the negative POH. See in the upper right corner, if the pH is 11.43, then the POH is 2.57, because those need to add together to give you 14. So the hydroxide ion concentration is simply 10 to the negative 2.57, which comes out to this number, 2.69 times 10 to the negative third. And that means that the only thing we don't know is the zinc ion concentration. So we can calculate that. And here it is, 4.1 times 10 to the negative 11th molar. And from the very top, because the coefficients in front of the zinc ion and the zinc hydroxide are both 1, if the concentration of zinc ion that's floating around is 4.1 times 10 to the negative 11th molar, then that means that the concentration of zinc hydroxide that dissolves also 4.1 times 10 to the negative 11th molar.